Good morning. I am not Guy Ernest. I am Randall Hunt. Guy Ernest was not able to come to Belgium, and I found that out about 24 hours ago. So I am now giving this talk. I know MXNet, and I use it in my day job, but I am certainly not the foremost expert on it. So if you have another talk that you would like to go to right now, I will not be offended if you get up and run away. It's your one and only chance. Okay. Before we dive into things, I'll just tell you a little bit about me. My name is Randall. I live in Los Angeles, where it's warm and nice, unlike here, where it's very cold. But the food is worse in LA, so things balance out. I used to work for a company called SpaceX in LA, and then before that, I worked at Amazon, and then before that, I worked at MongoDB, and then before that, I worked at NASA. So the next logical step for me after Amazon is obviously Blue Origin, since I keep flipping between startups or companies and space companies. I'm a software engineer. I have this title of technical evangelist, which means I just sort of chill and travel, and I get to work on code on my own pace. It's a great job. I strongly encourage you to pursue that as a role if it's something that interests you, because it's just very chill. Today we're going to kind of talk about who, if I were to poll the audience, how many people feel like they have a really good understanding of deep learning? Great. How many people feel like they know what MXNet is? How many people have used MXNet? So for the purposes of any video, that was 100% of the audience. Everybody's really jazzed. They're standing up. They're already clapping. Everything's going great. So my goal today is to give you an overview and a framework for how to think about deep learning problems. And we have 178 minutes. Don't worry, I'm not going to take all of that time. I'm hoping we'll get done a little bit faster than that. So first of all, what do you need to know about deep learning? The first thing, for those of you who have your laptops open and charging and all of that stuff, is I would say go ahead and go to this URL and launch the deep learning AMI. This is important to do now before we get into the rest of it, because it takes a few minutes to get started. So I'll leave this on screen for a little bit. It is really cold here. In Los Angeles, it's 75 degrees Fahrenheit. Fahrenheit's a temperature scale based on the human body, supposedly, whereas Celsius is based on something intelligent like water. But being from the United States, we don't do intelligent things very often. That's why we have to have artificial intelligence. Okay, everybody got that URL? Doesn't work? You're right, it doesn't work. Oh, I should probably get on the Wi-Fi. Let me see what the... So it works for me. But I'll just demonstrate what you're supposed to do. So you'll go to the AWS console. How many people are familiar with AWS, Amazon Web Services? Again, for the purposes of any video, that was 100% of the audience. Everybody's just really, really happy. This is called 1.5 factors of authentication. Instead of 2-factor authentication, it's 1.5. I can tell you how that magic trick works. It's the subject of my rejected PyCon talk. But what I want to do is I want to go to a region here. A region is kind of a set of data centers in a particular part of the world, in a particular geography. And I want to go to EC2, which gives me instances. Oh. Well, that ruined all of my jokes, didn't it? Here, let's try this again. Is that working? I have way too many tabs open. Let me get off of the page that has all of our secret stuff. Okay, so again, going to the AWS console. This is called 1.5 factors of authentication. And then we're going to go into EC2. EC2 is Elastic Compute Cloud. I don't name things. It's not my fault. I'm sorry. Essentially, you can launch a virtual private server with various networking options and all this other stuff. But what we're interested in doing right now is launching the deep learning AMI. So if I go over to this launch instance button and then I click this deep learning AMI, Ubuntu, blah, 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 and then I'll scroll down and I'll go to a GPU compute instance, and you'll see I have a lot of options. If anybody wants to email me, for the next 24 hours or so, if you shoot me an email at this email, I will send you a credit code for $100 or so to cover any costs that you incur from this workshop. After 24 hours, that deal is gone. So take it down, shoot me the email if you want the credit code, and I'll happily shoot you one because these can get expensive. So you'll see we have a couple different instance types here. We have the P3 16X large, which has 64 CPUs, 488 gigs of RAM, 25 gigabit per second networking. And then it also has the NVIDIA Volta GPUs, which, it's not that powerful, right? Like, it's not powerful at all. We don't need that machine. That's a joke. That's insanely powerful. All right. Everybody's laughing a lot. You should be laughing on the live stream. Okay. So we're not really going to launch one of those P3 16X larges just because we don't need it. We can go with like a P2 8X large, and even then we don't really need that. We could go all the way down to this P2X large. I'll configure my instance settings, add some storage. I'll add a full terabyte of data just in case we start doing some crazy stuff, and then we'll configure a security group. My security group is just open to everyone because that's how I roll. Don't do this in real life. It's a terrible practice. All right. And rather than launching this, I have already launched one. So I'm just going to go and look at the one that I already have. Here we go. Oh, and it is a P3. Man, my boss is going to be angry about that. So what I want to do is I want to set up an SSH tunnel. And the instructions for how to do this are down here in that blog post that I showed you earlier. This SSH tunnel, I'm sure many of you have seen this command before. Basically, all you're saying is, I want you to take port 888.88888 on my machine and send it to send port 88888 from the machine that I'm connecting to that same port. So I'll start that tunnel. And everything should be good. And then if I go, I'm just going to make sure I'm not running something else already. Okay. See, the issue is I do have a bunch of other models that I'm training on this machine, so it could get a little hairy here. Oh well. So I'm going to start a Jupyter Notebook right here in my home directory. And to do that, I'm just going to run Jupyter Notebook. And it's going to pop up a little token that I can click on. And then, boom, lo and behold, I am in my notebook. Everything is good. Everything is running. So do that. Follow the instructions here in parallel. And then it'll take a little while for everything to spin up. And while that's happening, I'm going to keep talking. And hopefully no one falls asleep. I know it's 9:30, 40. All right. So does everybody have the URL? I need everybody to shout yes. It's not working. Deep-learning-AMI blog. So if I go http bit.ly/deep-learning-AMI-blog. So So this is the URL, right? Let's see what happens. Oh no. Well, that's not inspiring, is it? Yeah, I'm wondering why when I click on it, it works. Weird. Yeah, I'm sure that's what it is. I just don't know how to use PowerPoint. Oh. I just want to point out, I did not make these slides. The person who was supposed to be giving this talk is stuck in Seattle. That's my excuse. Okay. Hopefully we've started making some progress here. Okay. Sorry about that, everybody. This is going to be a long day. Everybody made a little bit of progress? Awesome. It was a resounding yes, again, for the live stream. That's never going to get old. So, let's talk about MXNet. MXNet is one of many machine learning frameworks, but I think it kind of stands out from the rest of the machine learning frameworks in that it is a couple of different paradigms all mixed into one. So the idea behind MXNet is that you separate your computation from your kind of the description of your graph. So it's this idea of I have a graph or a set of things that I want to execute. I have, this idea I want to add variable A, variable B, and multiply it by variable C, and then do the dot matrix product with this matrix. And I don't actually have to have any of those values in order to define that graph. And then I can take that same structured execution and I can say, run this on a GPU, run this on 100 GPUs, run this on a heterogeneous cluster of millions of machines. And it works the exact same. The code is roughly the same, regardless of where I'm running it or how I'm running it. So it's pretty powerful in that regime, but you may not really have the contextual knowledge for what that means until you kind of understand what deep learning is. So deep learning at its core is this idea that we can take a bunch of labeled data and train a network similar to a human visual cortex is one type, like the convolutional neural network is one type of network that you could train. So it's this idea that you can take a network of, or you can take a set of labeled data, send it through a network, and iterate the weights and biases that go into each of the neurons in that network in order to build a new kind of network each time where the output is more and more like the labeled data that you're looking for. So if you guys have seen any computer vision APIs like recognition, I'll show you this really fast. And then there are other kinds of networks that aren't convolutional neural networks. There are other kinds of models that you can train, LSTMs, GANs, stuff like that. So this is an image, skateboard, sport, people. These are the labels that were detected in that image. We can look at another image, and it's like city, downtown, metropolis. I can do facial analysis. Looks like a face, appears to be female, age range. It's really funny when I upload my my headshot. The real question is, how old do you guys think I am? Ooh, Wi-Fi. This is my official headshot, by the way. Don't know how that happened. Very unfortunate. But we can call it to recognition, and it looks like a face, appears to be male, age range 35 to 53. I should maybe look into some skin cream or something. Smiling, appears to be happy, not wearing glasses. These are all powered by deep learning. So these are the kinds of things that you can do with deep learning, and I'll tell you about some like truly magical stuff that you can do later on, and you guys can try and break my network. But for now, we'll get back into it. And that's just an API that you can call, by the way. Has anybody used AWS recognition or Amazon recognition? Well, essentially, it's an API, and you say, hey, I have an image. I want you to tell me things about that image, and then you get back to like JSON data that tells you what that image is. Now, these were first proposed back in like 1957. There was like the perceptron, and there was this idea that you could take electromechanical inputs and encode data in it and build this network. And then in like the 1970s, there was this algorithm called backpropagation that people used to adjust the network over time and calculate what the cost was between your desired output and the actual output. And if this has been around this long, then why is it that only now it's getting popular, is the question that I commonly get. And this kind of brings us into the idea of the curse of dimensionality, where you have a ton of data. Like, imagine that image that I just uploaded. You have all the RGB values. So let's say it's, let's look and see what it is. So let's see, this is 2,000 by 3,000 pixels. So 2,000 times 3,000 times, let's say 3. That's 18 million values that you have. And then imagine that we were streaming a video at that same level. Then we'd have 27 frames per second, or 18 million pixels per second. And then of those 18 million inputs, we now need to kind of coerce down into a set of neurons in that second layer and those hidden layers. And then we have to figure out, okay, how do I take this dimension of time? And eventually it just gets very complex to perform the operations. Well, it doesn't become complex to perform the operations. It becomes very computationally intensive to perform the number of operations that we need to do in order to make this network work. So what you see here is kind of a 3D visualization of this idea, but it's important to understand that most of these networks are operating in far more than 3 dimensions. They can be operating in thousands upon thousands, millions upon millions of dimensions. And when you're calculating all of the different vectors and different functions that go into making the network activate on certain inputs and outputs, it is a complex set of computations that happen over and over and over again. And a common thing that happens is people will, and I'm going to warn you about this now because we'll get into it a little bit later, the 3D visualizations that I'm showing you are like really cool patterns for thinking about things, but they're not accurate because probability distributions across multiple complex dimensions, like say thousands of dimensions, do not map well to 3D space. And I'll explain that more later. But your intuition works okay for 3D space. After 3 dimensions, you know, rely on the math more than your intuition. So deep learning is kind of coming around again now because we finally have some advances in both algorithms, also in the data that we have available. So since the year 1991, we have produced more data every second of every day than all of humanity produced from the beginning of recorded history until 1985. So most of that is admittedly pictures of cats on the internet or tweets or Facebook posts, but you still understand we're producing a ton of data now, and there's the advantage of a lot of that data is labeled, and we can use that and we can do kind of cool stuff. Then with GPUs and various other forms of acceleration like FPGAs, stuff like that, in cloud computing, we kind of bring all of this deep learning stuff that used to be very expensive to do over to everybody. So a student in his or her dorm room now has the same capabilities of a Fortune 500 company or a Fortune 100 company or a Fortune 10 company, 10 years ago. And that's true. I mean, that's a true statement. You don't have an HR department, though. All right. And AWS kind of sits at the center of this. This is the required AWS plug that I'm supposed to put in. I do work for them. They're pretty cool. So this is an example of deep learning in the real world. These are our Kiva robotics that run our warehouses, and they each have a model that they run. So given a set of inputs, given the need to look for this item, I, as an individual robot, will go out, and I'm anthropomorphizing this a little bit, which will get freakier later. I will go out, I will find the shelf that I need to find, and then I will also communicate with all of my neighbors and with the network as a whole in order to orchestrate this kind of madness. And then we have these kind of drones, which can even file their own flight plans with the FAA. They can go and they can say, hey, I am delivering a package, this is my flight plan, so on and so forth. And this is all powered by deep learning. And then we have the Amazon Go store, which is I walk in, scan my phone, pick up whatever I want, and walk out. And this takes sensor fusion. And what it does is it allows us to basically, using RFID and computer vision and a ton of other different kinds of sensors, we can determine what each person is getting, and we can kind of eventually consistently swipe their credit card for them on their way out. It's like your AWS bill. Okay. These jokes are coming in too quick. Something that's particularly interesting to me, my brother got a heart transplant earlier this year, and the fact that deep learning and machine learning are two things that are enabling advances in the medical field is very, very interesting to me. So there's another example. This is Arteris, and what they do is they're able to create this four-dimensional flow of blood through hearts or even through the whole cardiovascular system. And they can rely on these models that they've trained in the cloud, as well as these solutions running in the cloud, and then just sort of render it on a very thin client in the doctor's office. Pretty powerful. And then there's another example where deep learning is now beating human doctors. So there's, if you take a scan of your retina, there are indications of whether or not you will get diabetes within that scan. And human doctors kind of suck at identifying that because they're human. And humans, I think we'll find out by the end of this that humans are just really bad at everything. But the deep learning thing can identify 100% of the time whether or not you're likely to develop diabetes based on these criteria. And it's very, very interesting that they were able to build that with just a fairly small training set. Then there's this common example. Does anybody have a Tesla? Okay. I live in Los Angeles, and I worked for SpaceX, so I obviously have a Tesla, and we do this kind of self-driving thing. And it's pretty crazy that this is, these are sensors that are going and saying, hey, these are humans, don't run over them, so on and so forth. And especially in these complex scenarios like this, you see, the car is stopping because there's a human walking. It's kind of organized chaos. And this is all, again, powered by deep learning. So a lot of these different things are modeled after these neural networks. They're modeled after literally neural networks in your mind. So there's this idea that you have these neurons and these synapses, and each neuron gets triggered when it is over a certain threshold. I'm not a biologist or a neuroscientist, so I'm not going to pretend like I know what this is. But what I can tell you is mathematically how it works. Now, the next series of animations that I'm going to show you are not mine. They're actually by somebody named Grant, whose last name I don't remember, I'm sorry, but I'll put it in the notes later. But Grant runs a YouTube channel called 3 Blue 1 Brown. Very, very useful, interesting stuff. So let's imagine, I'm going to start over, sorry. Let's imagine we have handwritten digits and we're trying to identify handwritten digits. So we have these 28 by 28 pixels, so 784 different neurons in our first layer. And then we're going and we're trying to build a network that will correctly identify the handwritten digits. So maybe your intuition tells you, okay, well, this top part, this little loopy bit of the 2, that'll activate, the loopy bit that I'm looking for. and then the 1, maybe that'll identify the long slanty bit that I'm looking for. And we can, in that first layer, we can break up the image into different pieces, and we can say, this is how this should work. And that's what your intuition will tell you. The network will learn however it wants to learn. So the way that our minds work is not necessarily at all how the network will work. Now, frequently, they do work that way. But I could pass in a completely random, like QR code style image into this, and it would very confidently tell me that it was a 5. So it's interesting stuff. Maybe it is a 5. So this is the idea of kind of bringing that first layer of 784 inputs down to just 16. And what we're doing is we're taking all 784 of those neurons, and we're fully connecting them to all 16 of our next set of neurons in this first hidden layer. And it ends up giving us like 13,000 and some 13,002 different kind of parameters that we're juggling around. So the weights are the kind of edges in this graph. And when we're training, what we're doing is we're finding the right weights and biases, and occasionally the right activation function for these neurons. Does this make sense, or am I just like way out of left field here? Everybody following? Did you know that if you speak out loud, you'll stay awake longer? Is everybody following? Oh, that was great. 100% of the audience answered. Everybody's really jazzed. They're just clapping. I'm sure you guys on the live stream are clapping too. Okay, so the way that this works, I can demonstrate. This is a slide, but this is a lot easier to understand than the slide. So you have this idea of you're kind of going through and you're trying to match each one of these edges. Now, you don't really go through like this. It's much easier to just have the edge, do the math, and see whether or not it matches, so you don't actually have to scan each time. And you can move the whole kind of kernel around. But at its core, this is kind of what's happening. Is it's going and it's building up this map, and it can do all of this information, all of this stuff in parallel. And then this is a convolutional neural network, yes. And this idea again of where it's going and scanning each time, yes, that happens, but it also happens all at once. It's not like it's doing each one of these operations serially. All of these operations are happening simultaneously. So this kind of brings you to the math section. I studied physics, and I worked briefly as a physicist at NASA before we blew up a bunch of rockets and I was fired. So I'm not going to talk about math because apparently I don't know anything about it. But essentially you have a set of inputs, a set of weights, and you sum those up and you have some sort of function. Like the typical function that people used to use was the sigmoid function. And that sigmoid function basically took a series of values from like a range, and it would bring them into a smaller range. And then you determine with some bias whether or not that individual neuron is going to activate. So a lot of people think of neurons as just holding a number, but they're actually holding a function. And that function is the result of all of the different weights and parameters going in, the bias, and the activation. So talking about activation functions, like I said before, a lot of people use sigmoid. Then there are other ones. I almost always use ReLU. I don't remember what it stands for. It's something like rectified linear unit, or who the hell knows. And the only reason I use that is because it works and it's really fast. And I don't know much more about it. Now, we can write code to simulate all of this ourselves. Like, we don't actually have to use a framework to do any of this work. Like, we could define it in Python. In fact, there's a really great book that does just that. But that's a lot of code, and I don't really want to cover it. So instead, I thought now that most of your deep learning AMIs are spun up, we would start looking at this kind of MNIST example. Does that sound good? Yeah. Okay. So, has everybody seen, by the way, I guarantee you almost every tutorial you go to on deep learning is going to start with this, but we're going to go through it fairly quickly, and then we're going to move on to some fun stuff. It's just this MNIST data set is like super common. It's what everybody uses to demonstrate how this stuff works. So I have installed, all of these prerequisites and stuff that it's talking about here. These are already installed on the deep learning AMI that you've spun up. So what you can do is, and MXNet already includes kind of the MNIST data set. So we will just go ahead and run this, which will download the MNIST data set and like pull it into stuff for me. Oh, and one point I forgot is in this process of training the network, you could run all of the samples at once, all of your training data at once, and calculate all the weights and biases from that set at one time, but it would also take forever. So what people do is they break things down into batches, and then they calculate the weights on those batches. Hopefully that batch is a representative sample. One of the things that people do to make sure those batches are representative is they kind of shuffle their data set. We don't really need to do that because it's already kind of set up, although I guess we do it here. So what I'm doing is I'm creating a batch size. I'm creating a training iterator, and that training iterator is going to use an indie array, which is our training data with our kind of training labels, and then we're going to say shuffle all of this, and then we have a validation set, and you typically save maybe 20% of your data, and you can play with those values. You typically save around 20% of your data for validating that your network learned correctly, which is you take 20% of the data that's labeled and you make sure you never pass it in to the network while you're training it so that it doesn't know it. It's not just memorizing things, it's actually learning how to identify stuff. So I'll run this. Now I'm going to create a symbol, and I'm going to cover what all of this is in a little bit. I'm just trying to demonstrate how this works. So I'll take this is not a convolutional neural network, by the way. This is a multi-layer perceptron. So we'll create a fully connected layer 1 with, I guess, 128 nodes or neurons. We have an activation function of rectified linear unit. We have a fully connected layer 2 with an activation function, again, of ReLU. So we'll create that. And then what I'll do is I'll just sort of point out what all of this does. So we take our data, we flatten it, we pass it into this fully connected layer, and then we pass it into this activation function to the next layer. We have another activation function, and then we have our output. And the output is just reading the labels 0 through 10, or 0 through 9. And then softmax is another function that we use to kind of bring things, bring these series of values down into a value that maps. And again, I will talk about all of this in a little bit. This is a really useful function when you're building networks. So that one line has saved me a tremendous amount of time when it comes to like visualizing and understanding my networks. If you're working with thousands upon thousands of layers, you can kind of dive deeper into the plot network API, and you can say, hey, I don't care about any of this. I just really want to know like what my input and my output looks like. So more complex networks you can't really visualize just because they have thousands upon thousands of layers. And then we can train it. So I will start training it. And you can see it's going, training. Da, 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 da. Dun, 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 dun. And I'll talk a little bit about what this training does in a second. And you can see we kind of arrive at like 97% accuracy, and we can test that on our testing data set. And looks like it's true. We could also do this using a convolutional neural network, which is more complex to explain. But again, we're just doing this kind of symbolic math, and we're creating these different activation functions telling us when the neurons that we have in this little square are going to activate. And again, we're just plotting it back out to this final layer. So this is more complex. I'm not going to go super into it, but same idea. I can train it, and I can train it on a GPU this time. It will actually go slower on the GPU than it will on the CPU, just because there's not enough data to really make full use of the GPU, and it takes time to send the data from the machine to the GPU. And you can see we arrive at like 0.998 accuracy, and then we can test that. Yeah, all good. So the convolutional neural network works a little bit better, but it might also have other constraints and stuff. So that's the basic MNIST example that everybody always shows when they are talking about deep learning. And now that we've knocked that out of the way, we can talk a little bit more about how these things learn. So what you're doing when you are training one of these networks is you have a cost function. And the cost function tells you how different your output from this first set of like randomly initialized weights and biases in your network is, how different that is from what you wanted it to be. So let's say I pass in the number 5 into my network, and I get out 0 activated, 3 activated, 4 activated, 9 activated. So I can take all of those different things that activated, and I can say, okay, these are off by this amount, this value, and I want to take that number, and I want to kind of iterate back through the network and make sure that I'm adjusting things so that that cost function is constantly going smaller. Now, the global maxima or the global minima, like the place where the network is like the most perfectly trained, is a really hard thing to find. Finding global minima in complex functions, again, this is where your intuition doesn't work so well, because what you're seeing here is a representation of a two-dimensional function, right? And even if I moved it into 3 dimensions, again, your intuition is not doing a great job of describing what it's actually like, because these are things that are operating in thousands of dimensions sometimes. But what you're trying to do is you're basically trying to calculate the slope and figure out, am I going down or am I going up? And you always want to be trending towards one of these local minima. So there are different kind of optimizers and ways of getting to that local minima. The most straightforward way, if you had all of your stuff available to you, if you had that whole set of like 13,002 different or 10,000 different handwritten digits as your sample, would be, okay, I want to make the optimal step each time. But because we're batching things and because we're doing different kinds of optimizations, we actually end up kind of drunkenly walking around down to this gradient, but we descend a lot faster in real time, which is advantageous. So that's kind of like this stochastic, I don't know how to pronounce that word, gradient descent. And then we have other kinds of finding the local minima kind of things. And you can understand that as these things trend towards these local minima, you start to have networks that recognize different features. Now with convolutional neural networks, you more frequently kind of start to find these features within each of the hidden layers. So maybe this first hidden layer is recognizing all of these different random edges. Maybe this second hidden layer is starting to recognize like whole pieces, these whole little kernels. And the third hidden layer is recognizing actual faces, or a hierarchy of information where it's cars, elephants, chairs, stuff like that. And this is a really useful cheat sheet for MXNet. Essentially, you can take all of the stuff that we've been talking about, creating fully connected networks, creating convolutions, pooling your data together, LSTMs, long-term, short-term memory, or even embedding. All of these different networks are typically just one call, one symbol in MXNet, and it allows you to do some pretty complex stuff with very simple code. So, why MXNet? It's very portable, so you can run it on iOS. Like if you've looked at CoreML, that's you can run MXNet with that. It's very high performance. It scales linearly across hundreds of GPUs. It's I don't know that it's the most open, but it's certainly open. It's an Apache project. It's programmable with a couple of different interfaces. So there's also the gluon interface, which somebody asked about earlier, and I'll dive into that a little bit later. But that's more of like an imperative
idea, where you can just sort of go through and declare everything in real time and have it execute. It's got a very diverse community of both industry and academia. So if you look at the top contributors for MXNet, it's kind of all over the place. You know, Tesla, AWS, Stanford, Apple, all kinds of people. And it's kind of the fourth deep learning framework in terms of popularity. Cafe is kind of where, or CAF, I don't know how to pronounce it actually, is where like the old school deep learning people tend to hang out. They're the people who are like the masters of this. So if somebody says they know CAF or Cafe really well, they're probably really good at this, and they probably know all the other frameworks really well too. So look for those people and try and learn from them. TensorFlow is newer, it's super useful, and TensorFlow is also built into the deep learning AMI. So while I'm talking about MXNet today, you can use TensorFlow very easily on AWS, and I think AWS is probably where most TensorFlow workloads are deployed. You can scale to multiple GPUs with MXNet pretty easily. So if you look at what the ideal kind of line would be as you add more GPUs, you can see with these different networks, Inception, ResNet, and AlexNet. I always call it AlexaNet because I work for Amazon, and Alexa is just a thing that I say too often. But it's AlexNet. I've made that mistake probably 100 times. And I was determined not to make it today, but I already made it. So you can take all that info and you can kind of use that to determine whether or not adding a GPU is useful, based on the different types of networks that these are. That slide is just broken, I'm sorry. So it's pretty darn efficient. And with that said, let's talk about how it all works. So the core piece that you're working with typically is an ND array. It's an n-dimensional array, and it's basically just, I have some data. Has anybody used NumPy? So it's very similar to a NumPy array. It's like, I have this data, it's in this shape, and it's this type. And then the next thing that we have is the symbol. And this is a symbolic expression for how a set of computation should unfold. So if I wanted to take one ND array and another ND array and I wanted to multiply them together or do the dot matrix product, whatever, that would be one kind of symbol. Then we have modules, and modules are both intermediate and high-level interfaces for different kinds of training and interfaces. Then we have loading data and binding data. So that's feed forward is the common API call for that kind of stuff, where you have a bunch of data in these ND arrays and you finally want to feed it into these modules that you've created or into these symbols that you've created. So you feed forward, send that ND array through your network, and you get this output. And then we have kind of this mixed programming approach where we define the network symbolically and the data separately. And those are the end of my slides, thankfully. And we can get into some crazy stuff. So, again, I was not the original speaker for this. I found out 24 hours ago I was doing this. So I have hundreds of different examples that I could go into. I just finished doing a deep learning series on Twitch TV that you guys can watch. And we have a bunch of different episodes. One of the things that we created was whether or not an image is me. So we can do that. We can talk about sentiment analysis. We can do this one really fun one that I liked, which is predict places. Or I have a whole set of labs that you guys can download. Some are for distributed computing. Some are for sentiment analysis. Some are for building out giant distributed clusters. It's really up to you guys where we go from here. Or we can kind of end the video and do some Q&A style stuff. What is of the interest to the audience? Everybody just immediately started talking and jumping up and down, and it's just chaos. So I'm sorry for those on the live stream that you guys have to hear all this chaos right now. Predict places, that's a fun thing. Predict places? Okay. Make it fun. Okay. So, so I'm going to download all this data. This will take a hot second. Basically, this is from a paper. I wish I knew the name of the paper, but I don't. But it is a set of images that are labeled with their geographical coordinates. And this will take a second. So while do we have any questions so far? I'm from New York, but I live in Los Angeles, so I speak English quickly, and I'm really hard to understand because I don't enunciate, because in Los Angeles you don't really want to communicate with other people. So if you guys are having trouble following me, that's why. Desperately need to move back to New York. Any questions? Yes.
In a previous slide, you said that MXNet was optimized to run for AWS. What does it need?
I mean, it can run anywhere. It doesn't have to run on AWS, but we definitely spend a significant amount of time making sure that MXNet and TensorFlow and all of these other frameworks run really, really well on AWS. So yes, MXNet is optimized to run on AWS, but so are all of the other deep learning frameworks. And as far as what that means, it means, down to like instruction set, we're looking at how we can improve the speed of what's happening. Does that answer your question?
Yeah. My question is, there is on AWS some, for example, specific hardware that can accelerate more?
Do we have specific hardware that can accelerate more? No, not really. So, I mean, we have FPGA style instances. So if you wanted to... Mm-hmm. It can also run on Lambda, which is the talk that was actually accepted here that didn't involve somebody canceling 24 hours in advance, which is the talk that I'm prepared to give. So you guys should come to my Lambda talk. Just throwing that out there. So, yeah, so it can run pretty much anywhere. So what we're going to do now is we're going to we're going to load in this existing module that we have, this pre-trained model, and we're going to load it from, I think this should probably be a 12. Yeah, that should be a 12. But we don't use it. I just hard-coded 12 in because I don't know how to write Python. And when we load in an existing module, what we're doing is we're just saying bind all of this data, and this is the shape of the data, and we're not going to be training, so we're not going to be using this model to go back through and like fine-tuning it. We're really just going to be running predictions with it. And then this is just creating a set of truths values using a grid file. So oops. So if we look at this grids.txt, it's really just a set of labels. Then we define the distance function. This is not a hard thing to do. And then these are just things that, these are helpful functions that allow me to go through, grab an image, process it, and get it into the network and all that stuff. Not very difficult. So the first thing we might want to do is I have this image in my data set. So I want to grab it, and then I want to see where it is. That didn't look promising. So I need to restore the what? No, the tunnel is still there, I believe. So tunnel running on one port, me running on other port, control connection, doing all that stuff for me. It's the trick. So this is the image here. This is from Hoover Dam, I think. Yeah, that looks right. And you can see the first prediction puts us squarely at the Hoover Dam. So not bad. I was thinking we could take an image that I took yesterday. Unfortunately, that will involve me hiding my screen because I don't know what other images are. I was in Amsterdam yesterday and ate a lot of really good food. Oh no. None of my images have been uploaded yet. So I'll just grab some from Facebook. Those are all definitely safe. You guys are welcome to follow me on Facebook. Ooh, that might be a good one to use. So lots of trains to get here. So I need to find one not food picture. That might work. Obviously, I had a really good trip so far. I think we'll use this one. So we'll say save image as. I'm going to crop it into a dimension here. Tools. That's not right. How do I crop something? You can tell I don't do a lot of like image work. Okay, that's what I'm going to use. So, sure. And then we want to SCP from downloads. What did I call this? Amsterdam.png. Oops. Everything is messed up. Here's SCP, or sorry. I wish there were a way to just drag and drop this. I wonder if that would work. Is iTerm smart enough to do that? Nope. Okay, so SCP downloads amsterdam.png.
I was going to guess the location from the file name.
I mean, I can make the file name totally random if you want. Why isn't this working? This is the fun part. This is what all of my Twitch streams look like, by the way. Ta-da! Oh well, it worked. I don't know why I did it again, because I know that it worked. Anyway. Okay. So we'll make this a random name, like... yeah, 123.png. That way I'll be able to type it. And I actually just realized that what I'm trying to do is not going to work. And the reason for that is I have completely forgotten what dimensions and stuff I'm supposed to put this image into. So if you guys want to bear with me for a little bit, I will figure it out. Yeah, so this is a good break time if anybody wants to get a break. Images. D66. JPEG. There used to be this app called like JPEG Info. We can always just how to get image dimensions from, yeah, 10 minutes. Go for it. Oh, you're really planning on coming back. Wow. I'm surprised. You can also just leave. I would not be offended. How to get image dimensions from CLI and... Yeah, I'm just trying to get the dimensions that I need to put the image into. File D66. 500 by 375. So then I can be like, convert. Nope. I think I need image magic for that.
Why does the image size matter?
Because the network has been trained on a certain set of inputs of like apparently 500 by 375 pixels. So I need to pass in that set of inputs to the network for it to properly evaluate things. So I'll resize here. Tools, adjust size, 500. And then we need to take off 116. Nope, sorry. We need to take off 41 pixels from the bottom. So does that look like 41 pixels? Damn it. I have no idea how to use these things. Really delicate work here. I think the image size we had would have been fine. Oh well. Okay, so I'm going to move. Oh, and I probably should have saved it as a JPEG. So I want JPEG, and I'm just going to leave it at whatever size it was, so long as it's 500. And we'll call this Amsterdam1. We'll open Amsterdam1, and then we'll say adjust size. Perfect. I think this will work. Even though it's not the right size. SCP Amsterdam1.jpg. Should probably take off that other G. And then move Amsterdam1.jpg to images. 123.jpg. And then we'll take all of this again. And we will say use 123.jpg, and let's see what it does. Uh-oh. I might need to reload those images somewhere. So let's go look at our predict and evaluate method and see what I did there. That's the right one. I might need to recalculate all of these ground truths again. I really wish I hadn't saved the notebook before I deleted the part of this that worked. Okay, I'm going to look up the answer. I don't remember. I can take any questions while I'm doing this. Just start talking. How is it supposed to work? Is it supposed to say that this image that I had is in Amsterdam? Even though we haven't given it any information about where in the world I am. Like if I showed it a picture of Tokyo, it would tell me that I was in Tokyo. And it does work. But again, 24 hours of preparation. Less. Because Amsterdam.
Even for cities that are not in the training data?
So it doesn't give you the name of the city. It gives you the geographical coordinates. And yes, so even for things that are not in that. Now I'm not saying it'll be 100% accurate, but it is pretty magical to watch that work. So this is built on top of a paper from Berkeley, Multimedia Berkeley. And it's built on top of the media eval. Placing benchmark. And then it uses the AWS Multimedia Commons dataset to geographically categorize the YFCC 100M images. So it has a pretty large training set. And you can look at this. If you just go to github.com/multimedia-berkeley, you can see this running. I'm just trying to figure out where the stuff to launch this is.
The gradient descent, how big is the local minimum problem? Like, if you constantly find local minima instead of the global minima?
Most of the local minima are roughly equivalent. Now, I mean, that's a gross statement, but finding any local minima is normally better than, you would do otherwise. So most people don't worry about like getting over the humps between different local minima. There is obviously a global minima somewhere, but the general idea is if your network is well designed, most of the local minima should be roughly equivalent. Now you can try different things, so you can there was this really cool paper that was published recently where they adjusted the hyperparameters of a training network with different kinds of shuffling, different kinds of like folds. So you would take 10% of your data and validate it on 90% of your data, and then you would do cross-training. So you would have one part of your model trained on like 50% of your data and another part trained on 20% of your data, and you would just kind of iterate. And that is like one of the techniques that people are pursuing to try and find other local minima. But typically, if you find any local minima, you're good to go. So there is some impact, but it's not significant. So I think I've got this working now. I think I've got this working. Does anybody remember what we called it? Was it 123 JPEG? Oh. Yeah, that was totally on purpose. No, I wish I'd had it plugged in. Okay, so moment of truth. And I'm sorry that I had to put all of that away, but I had to look at my email to find links and stuff. And we have this conference coming up called AWS reInvent, and there's all kinds of secret stuff. So we got to figure out where these different things are. So we'll plot it. So, not super accurate, but still, it is. That's an image that I took from my camera roll, like relatively little modification. We could try another one. I could, so I could kind of dive deep. There are a bunch of different tools actually for kind of diving into the network, and what layers it's going to, but I don't have the expertise or the preparedness to dive into that today. So instead, we're just going to try another image of a landscape from my camera roll and hope that that one works. I think this is San Francisco, so we'll try that one. And then I'll rename this sf.jpg, and then we'll do AWS. Yeah. We're going to try without doing that. I don't think that'll work very well, but we'll try it. I'm hoping that this code will properly kind of resize things. I've already lost where I was, sorry. So AWS, SCP, sf.jpg. Move sf.jpg, or sorry. move sf.jpg into images, right? That's where we were keeping everything. And we'll change this to SF. Oh, and it's also upside down. I'm pretty sure this is San Francisco and not... Oh, yeah, you're right. Wait, if number 1 is in the right place? No, okay. I wonder where number 1 is. So it's got the landmark of like the Empire State Building, and that's where it thinks it is. I'm pretty sure this is San Francisco. Let me look again. That's definitely San Francisco. Okay. So I normally have, latitude and longitude coordinates kept in my images. So I promise we'll find one that works. Okay. This is Paris, obviously. Okay. This has to work. So I'm going to call this one... Yes. Or do you? Like the network is trained on tons of pictures of sky, and maybe the sky looks different in different places. Like we have the human intuition for how these networks should be able to determine where something is. And when you actually dive into the network, it's completely like you cannot understand like how it's deriving some of these locations. So SCP, come on. This is a very long talk. How are there 109 minutes left?
You explain how to design a network?
How to design a network?
How many neurons and how many layers?
Yeah, so what I typically do is I find a paper, an academic paper that's already done something similar to what I want to do, and then I copy their network, and then I make a bunch of different modifications. Maybe I change the number of layers, or maybe I have a different activation function based on like the output of one layer, and sometimes I'll change. The first thing that you start tinkering with are like the batch size and the learning rate. After the batch size and the learning rate, you have to actually kind of get into the network itself, and there are other parameters that you tune. But I've never really had much success training a network without some sort of idea of what somebody else has done. Like you can totally go and do that if you know a lot about machine learning, but that's not me. So I just steal from academic papers and tune those different networks to do what I want. Like we have to get onto our we have to get onto our network at Amazon. A little token, like a hardware token that we have to read. And I built a network that would read that hardware token, take out the numbers from it, and type them into my computer for me. And that's the extent of like success that I've had building my own network. Again, just want to point out, I was not the person who was supposed to give this talk 24 hours ago. And after this works, because we're determined to make it work, I even named it Works, we are going to kind of close things down. Works. Yeah! All right, cool. Sorry. So, I mean, you can do things whenever there are like big landmarks like that. I'm happy to take like any challenges for this network because it's pretty well trained and it can do some pretty magical stuff. Like this is from my camera load. This isn't like some picture from the internet. This is literally just a picture that I took last year on October 2nd. Okay, that's really all that I wanted to show off. There are a couple kind of calls to action that I have for you. So these are the sort of calls to action. All of these different pages and websites will teach you things. I will put these in the notes for the talk later. I'd strongly encourage you guys to go check out other talks that didn't have their speaker replaced 24 hours ago. But if you want to talk about things, can we end the video and then we can do talking things, Mr. Audio person? Can we end the video and everything? And perfect. Great. All right, thanks.